Hello, this video is Math 2414, sample problems for the final exam. So let's take a look at number one. This is a surface area of revolution problem, and we're revolving this around the x-axis. And what you have to remember here is that the r of x, here's the formula, the r of x will be whatever f of x your function is, your height, as a function of x, not just the variable y, but everything's in terms of x, so it has to be f of x. Whereas you'll see in the next problem, when it's the y-axis, r of x will just be x. So it has to be, it's either f of x or x, depending upon which axis it's revolving around. So this one gets a little messy on the algebra part of this, but the integration itself is pretty basic. In fact, I went through all the mechanics of this. At the point you could have used the graphing calculator to do this, the numerical integration, if you wanted to. But I went ahead and worked it out just in case someone wanted to see it. I'll show you. Let's focus on the setup, then I'll show you what we could have done here. In fact, I might go ahead and bring up the calculator here. So we need the derivative of your function. So the derivative of x cubed over 5 would be 3x squared over 5. And the formula is going to be 2 pi. The limits of integration would be 0 to 2. And then 1/5 x cubed is, of course, is x cubed over 5. It looks like I erased something here. No, I didn't. Okay. All right, so... And then the square root, which I just rewrote as to the 1/2 power. 1 plus the derivative itself just squared. So 1 plus 3x squared over 5 squared, and then all that to the square root. And at this point, so the calculator popped up there, but so, you have this, and you could put this directly in the calculator as is, which I think I'll do real quick just to show you. Now, what I like to do is when I do these in the calculator course, I just leave the pi off of it and realize that that pi is going to be part of the answer. And I'll go ahead and see here I went ahead and just squared the 3x squared over 5 and got 9x to the 4th over 25. So I'll go ahead and put this one in the calculator. So I would clear this, and I'd go 2 over 5 times the integral of x cubed and then times I'll just put the square root in there, 1 plus 9x to the 4th. I'll make this screen a little bigger. I don't need all those commands down there. Right here, and just divide that by 25. Before I go over the dx, let me just double check that looks okay. All right. Very good. So now we're going to give it a dx. And I'm going to hit enter. I want to go math, frac, and there we go. Now sometimes it depends on the integral, it won't necessarily convert it to a fraction, but in that case you can convert your answers to decimal and then see which one would match. You could go that approach, but this one did. It converted it to 2072 over 675 with pi being part of the answer. Like I said, I did not include the pi because I knew I would just stick it in there. And then there's the answer right there. But here's, I'll go through this real quick, or maybe, I don't know, maybe I won't here, we'll see. But yeah, I'll do it real quick. But you let your u be what's on the inside, if you're doing it the manual way here. Take the derivative, And then, of course, the reciprocal of that fraction is what's going to go outside the integral. Because I didn't write the step, but I would solve for dx, x cubed dx would equal 25 over 36 du. I'm a big fan of changing my limits of integration because I never have to go back to x again that way. So I put in the 2 and I put in the 0 right up here for x and got those two results. And then the antiderivative of u to the 1/2 would just be 2/3 u to the 3/2. And all this stuff just combines by reducing fractions into 5 pi over 18. And then that combines one more step into 5 pi over 27 because 2 over 18 is 9. And then put in 169 over 25 to the 3/2 minus 1 to the 3/2. And the reason why this one works out to be an exact answer is because 169 divided by 25 actually has a rational number square root. It's 13 over 5. So it's not like the square root of 10 or something like that. You can actually take the square root of that and you get 13 over 5. And then you would have to raise that to the 3rd power. And it all works out being simplifies to 272 over 675. So very good. Number 2, surface area. This time we're revolving around the y-axis. So r of x would equal x. And that's the only difference. Still the same formula. It's just x will go in front of the radical. Now these problems and any kind of problem you would see on one of my tests, especially being the final exam, of course, is it's designed where it can be worked out manually. It doesn't have to be done in the calculator. So that's, if you set this up and you don't see u sub working or something like that, that probably could be the mistake right there. You used the wrong thing here. But yeah, they are designed where they can be solved manually. Now this one I didn't even put in the calculator because I knew it was going to have radical answers, so I just did it that way. But like I said, you can still do it and then just check the decimal answers and see what matches. So my f of x, which x squared over 4, makes the derivative of 2x over 4, which is x over 2. We're going from 6 to 8. So we're going 2 pi from 6 to 8. X is what r of x is, times 1 plus x over 2 itself squared, all that to the 1/2 power. And you could type that right into the calculator if you wanted to, but let's go ahead and we'll work this one out. So x over 2 squared becomes x squared over 4. And then, so u is going to be 1 plus x squared over 4. And then du is x over 2 dx. Change the limits of integration. U of 8, put 8 in here, you'll get 17. You put 6 in here, you'll get 10. And then I didn't show the step where you bring the 2 over. So x dx equals 2 du. So we have a 2 pi, which of course we started with. Now that 2 is coming from this 2 right here. So we have that 2. Now we're going from 10 to 17, u to the 1/2. So the antiderivative of u to the 1/2, of course, is 2/3 u to the 3/2. Now that, of course, becomes 4 pi. So 4 pi times 2/3 is just 8 pi over 3. And then when you put in 17 and you put in 10, it's 17 to the 3/2 minus 10 to the 3/2. Now the only thing, that doesn't really simplify that well, but what you might see sometimes on answer choices and multiple choice is, mathematically, 17 to the 3/2 is equivalent to 17 times the square root of 17. So you would see it as 17 times the square root of 17 minus 10 times the square root of 10. But the radical idea is not going away on this one like it did on the last one, which just happened to have a perfect square root. So you might see it written with radicals. But essentially, that's the answer right there. All right. Number 3, we're going to do a volume of solid of revolution. We're going to do a shell method. Later on in the few problems down, you're going to see a disk washer method. So let's show one kind of with the shell method. And really, when you're doing this on the exam, even if it tells you a method, it may just say solve the problem by either method. But even if it tells you, if you think the other method works better, then you can use it. I can't really stop you from using it. But this way I'm showing you one of each kind. So it's between y equals 2x cubed and y equals 2x for x greater than or equal to 0. These are even if you don't have an easy graphing calculator, these aren't hard functions to make a sketch of. Well, especially the line is easy. But they meet here at 1 for x and then 2 for y. You could actually solve that if you needed to. Wouldn't be hard if you set those two equations equal to each other. They're going to intersect at 0 and they're going to intersect at 1. Okay. So now this is, you got to, when you look at the washer method later, when you we're going around the y-axis. For the shell method, it's always the opposite variable. So if you're going around the y-axis, you're integrating with respect to x. And if you're going around the x-axis, you're integrating with respect to y. That's where it's a little confusing between the two methods. The h of x, this distance out would just be x. You could expect h of x to be x for any problem that I ask. And you can expect h of y to be y if it was the other way. And the p of x, in this case, it's the vertical distance as a function of x. So let's say if the graph was going all the way down to the x-axis where the bottom one was just 0, you would only have one thing here. But we have to subtract the two. And it's upper minus lower. It's 2x minus 2x cubed. So I drew that what they call that representative rectangle. But this rectangle, and once again, in the shell method, it's parallel to your axis of revolution. In the disc and washer method, it's perpendicular to your axis. This is the way you would draw it, as if this was going around the x-axis. But this is going around the y, because it's vertical, so it spins around the y-axis like this. But you still do upper minus lower. It would be right minus left if it was going around the y-axis. I mean the x-axis, I'm sorry. Right minus left, but then the opposite of that is true. If it's the washer method, disc method, it'd be right minus left around the y-axis, and it would be upper minus lower around the x. I worked this out manually. This is a pretty easy integral to set up to do in the calculator real quick. See, I left the pi. I meant to put the 2 from the formula. Oh, I didn't include the formula here. Let me pause for a second and put that. So I brought up the notes real quick. So here you can see that there's the formula. In fact, I'll snip this out of here. So you can see that x is there. Oh, now if I can find room for it somewhere. You see, so it's p of x times h of x, and it's 2 pi for this one. The disc and washer method only has 1 pi in that formula. I think I'll shrink this down a little bit. So it's going to be the inner. So anyway, what I was saying before I caught that thing is that I didn't put the 2 in front of the integral. It didn't matter mathematically, but like I said before, I leave the pi off of there, but I just hand wrote it in there. But I forgot to put I didn't put the 2 in front of the integral, so I just put a multiplied times 2 at the end, which is fine. I got the 2, or I could have just added whatever. But anyway, I probably would have put the 2 in front here had I caught it. But I didn't feel like retyping it just for that reason. So it's 0 to 1, x times 2x minus 2x cubed dx2, and then I did the math frac, and then it produces 8 over 15. Tack on the pi, and there's your answer. Here it is, kind of worked out. So obviously the way to integrate this is you would distribute through the parentheses. This is not a square root this time, so yeah, obviously you can't do that for the first two problems because the formula has a radical and you can't distribute through the radical unless you're using a radical to distribute through the radical. But anyway, here, so you just send this through. So that's pretty easy. This is just a basic Cal 1 integral, really. Nothing too fancy. Well, so was the other two, but the other two were also. And so there we go, 2x cubed over 3, 2x5 over 5, 2 pi. Put in 1, put in 0. 0 will be 0. 2 pi times 2/3 minus 2/5. 2 pi, 4 over 15. There's 8 pi over 15. So if you like doing it manually, there's what you would come up with. Okay, these next two problems are basically inverse trig functions that you might have seen in Cal 1, but these certainly can be classified under the section in the Larson book on 8.1 Basic Integration Rules, which is a summary of important techniques. So, all right, this one's not too bad here. Let's take a look. So you've got to set this up in such a way that your du, has to be x to the first power. So in that case, your u needs to be x squared because the derivative of x squared is 2x, and that makes it x to the first power. So in this case, the u would be 4x squared because two things. When you square it, it gives you the 16x to the fourth. And then when you take the derivative of it, that gives you 8x dx. And that gives us 1/8 du over 1 plus u squared. And actually, this is inverse tangent. And if this would have been anything other than 1, because if a squared is 1, that means a is 1. A squared plus u squared means we would add a 1 over a and then u over a here in the parentheses. But since a is 1, those denominators would go away. So you end up with 1/8 tan inverse or arctan, I just went with tan inverse to match the answers, 4x squared plus c. Let's take a look at number 5. Same idea. It won't be arctan though, but because of the square root, obviously. But I need u to be e to the x because when I differentiate e to the x, I will get e to the x, and then u squared would actually be e to the 2x. So it fits perfectly, and you have du over the square root of 1 minus u squared is arc sine, or inverse sine. Now, it would be u over a. There wouldn't be a 1 over a in front like there is for the tangent, but it is u over a. And you can look all those back up again easily enough. But that would be u over a, but a happens to be 1, so there's nothing in the denominator. So it'd be sine inverse of e to the x plus c. Now this one, we have to complete the square. I mentioned the next two problems earlier. I said 4 and 5. I forgot about this one. I'm not sure. Let's see if there's anything. And the next one has a bit of a division to it. So, okay. A little bit more than I thought here. So we have to complete the square. So if we add 9, we then subtract 9 to balance it out. And that would convert it into x plus 3 squared plus 9. Remember, you're always adding half of the middle term squared. So half of 6 is 3. 3 squared is 9. And you rewrite it as dx over x plus 3 squared plus 9. Now, I didn't write this down but over here, but a would be 3, square root of 9. So u is x plus 3. Du would just then be dx, so there's nothing to adjust there. A would be 3. So it's 1 over a, 1/3, inverse tangent of u over a, x plus 3 over 3, plus c. Number 4 requires long division of polynomials before we can integrate it, because that is an improper fraction, meaning the power on top is greater than or equal to power on the bottom. This idea also came up in the partial fractions content. I'm not saying it's going to be on here or on the test per se, but it's an idea we should be familiar with. Have to divide to be able to integrate this. So we take t squared plus 16 into 4t cubed plus t squared plus 64t. So then we look at this as how much does t squared go into 4t cubed. So basically it's 4t cubed divided by t squared, which is 4t. 4t cubed, and then 1 times 16. 4t times 16, excuse me. Sorry. 4t times 16 would be 64t. And when you're dividing, you're always subtracting. Now, the idea is that first term should always cancel. That's just a coincidence that the 64t canceled. That was not planned. And then we're left with t squared. And we have one more division step to do. T squared divided by t squared would be 1. So there's your 1. So you multiply 1 times t squared plus 16. And because we're subtracting, of course, the t squares cancel, but that is negative 16. Because essentially it's just 0 minus 16. And then we're left with this result. Quotient, remainder. So we're integrating 4t plus 1 minus 16 over t squared plus 16. So the first two terms are just basic antiderivatives. 4t would be 2t squared. 1 would be t. 16. And then this is arctan, where a would be 4. So it's 1 over 4 arctan, or tan inverse, t over 4, and then all plus c. And there it is right there, answer B. Number 8. This is the derivative of a hyperbolic function. Okay. And you have to be careful with these hyperbolics because the derivatives are similar to trig derivatives, but some are not quite the same, plus and minus wise. Like, for example, the derivative of hyperbolic cosine is actually positive hyperbolic sine, not negative like it is with regular sine and cosine. So this is just a chain rule. So you'd bring the 2 down in front and leave that as tan of 9x. Then you're taking the derivative of tan of 9x. Now that's going to have another chain rule component. So the derivative of tan of 9x, we'll take the derivative of 9x, which will be 9, and the derivative of hyperbolic tan is hyperbolic secant squared. So so there's a 2 and a 9, and of course they multiply those together to get 18. So it's just a chain rule derivative using hyperbolic functions. Find the general solution of the differential equation. All right, this is where we have to use separation of variables. So we've got to get the x's on one side and the y's on the other. So I brought the dx up here and moved it up and over. And now I got a y I've got to get rid of. Well, dividing both sides by e to the negative y is exactly the same thing as just multiplying e to the y. So if I did dividing by e to the negative y would just bring it up and make it e to the y right here. So either way you look at it, you're going to end up with this result right here. The antiderivative of e to the y dy would just be e to the y. The antiderivative of 4x cubed would be x to the 4th plus c. Technically, that's actually solved, but you can see the answer choices are solving it in terms of y. That's how you can tell. So I didn't actually write this step, but I'll just say it. So you natural log both sides to get rid of that e. So when you natural log the left side, you just have y, and then you have ln of x to the 4th plus c. Now, this is not like when you have like e to the x to the 4th plus c, where you bring out the c. This isn't like that. All other functions work this way. where the plus c would be in parentheses like that. It doesn't come out. And that would basically be the solution for that one. Number 10. So you bring the dx up and over. Notice I divided by both sides here by cosine squared of y to get it over. And one thing we learned in the trig integration section and thing is that you never dividing by a trig function for integration purposes is not useful at all. So that means you always bring it up and make it its reciprocal trig function. So dy over cosine of squared y can't be integrated that way. You bring it up and you make it secant squared of y. And then the right side we just have 8x to the 7th dx. So you integrate both sides. Secant squared of y has a convenient antiderivative of tangent of y. And then 8x to the 7th dx would just be x to the 8th plus c. And then to solve for y, you would apply inverse tan to both sides. So inverse tan takes out tan and leaves y. And then the right side, it would just be tan inverse of 8 x to the 8th plus c. And see that c also stays in the parentheses. And there we go. Answer A. And here's another one that's an initial value problem, which means we separate the variables and then we have this information y of 0 equals 2. That allows us to actually solve and get a numerical value for c. So that's the difference. That the last two problems were what you call general solutions. This is actually called a particular solution. So let's see what we have. And I wrote y prime is dy dt. Bring the dt up and over. Divide both sides by y. Of course, if you can figure that out all in one step, it's up to you. It could save you a little work there. Not much. So I have dy over y equals 4t dt. I'm ready to integrate both those sides. So dy over y would be natural log of y. The right side would just be 2t squared plus c. And then now we're going to e both sides. So you have e to the ln of y, and here e to the 2t squared plus c. So here's what I mentioned a couple of problems ago. Now this is that when it's e raised to that c, that's because since you can write it like this, properties of exponents allow you to do this. Write it this way. And e to the c, because e is just a number, e to the c is still just considered to be a constant number. So you can just write it as e to the c as c, and you end up with this. But only with this. We had one problem above there that had a natural log with a c and an inverse tangent with a c in the parentheses. We did not remove the c there. You could not do that. But here you can. And that's pretty much standard practice to do this. So the general solution of this would be y equals ce to the 2t squared. And then now we put in 0 for t and 2 for y. So you put in 0 right here for t, 2 for y. That makes all that e to the 0, which equals 1. So basically you have 2 equals c times 1. It's kind of a weird way I wrote that, though. I should have written c equals 2. But anyway, hopefully that's not too confusing. But c equals 2. And y equals 2e to the 2t squared. There it is, right there. Very good. Let's take a look at number 12. Going to find the area between two curves. Graphing these is not a bad idea. You can do it actually without graphing. Well, graphing helps you tell for sure if there's more than one region of integration. This one is only one region of integration. Now you can use the calculator features, I guess, to figure out these points of intersection, but here's how you do it algebraically. It's not difficult. Certainly for a Calculus 2 student, it should not be difficult. You set the two functions equal to each other. Two x's cancel. you end up with x squared equals 4. And that means x equals plus or minus 2. So right down here, they're crossing at negative 2 for x. And they're crossing again at positive 2. Let's see. So we have negative 2 to 2, upper minus lower. If you get them in the wrong order, you're going to get a negative answer, and area can't be negative, just like volume can't be negative. So the upper is the parabola. So it's 2x minus x squared minus 2x minus 4 dx. I haven't, and then that simplifies to this. And I didn't work it out, but it's pretty easy. It would be negative x cubed over 3 plus 4x, plug in 2, plug in negative 2. This is the, been around with, this is the old school way. You had to do F and Int before the more modern calculators. So I'm going to go ahead and, before they started putting the integral sign in there. So if you actually were using like a TI-83 or something like that, you could see how that would be entered. Now you could actually have typed this in there the way it was originally, but I'm going to go ahead and use the reduced form just so I don't have to put in as much, and I'll show you what I mean here when I go back to the page. I shouldn't say reduced, it's not the right mathematical term. The simplified form, where you combine those two things together. That's not the correct wording on my part. 32 over 3. But what I'm saying is that you could type this all in there like that, and obviously that would be fine. But I figured it's easier just to type this in there, fewer terms. And there it is, 32 over 3. Old school way, new school way, every way possible. Gives you 32 over 3 for that answer. All right.